In 2014, a naval architect sat at a drafting table in a research office affiliated with the University of Queensland School of Engineering. On the desk was a printout of 6 verses from Genesis chapter 6, verses 14 through 16. The verses contained what appeared to be a construction specification. Material: gopher wood, a term whose botanical identity remains disputed in the scholarly literature, but whose structural properties can be bracketed between cypress, cedar, and teak, based on species available in the ancient Near East. Dimensions: 300 cubits long, 50 cubits wide, 30 cubits high. Internal layout: 3 decks, internal compartments described with the Hebrew word ken, a door set in the side, and an opening at the top of 1 cubit. Waterproofing method: pitch it within and without with pitch, bitumen, a naturally occurring hydrocarbon whose waterproofing properties are extensively documented in Mesopotamian construction records. The naval architect was not conducting a theological exercise. The architect was conducting a hole stability analysis. The cubit measurement was converted to meters using the most conservative scholarly estimate of the ancient cubit at 44.5 centimeters. The resulting dimensions were entered into hole stability software: 133.5 meters long, 22.25 meters wide, 13.35 meters high. The software computed the metacentric height, the single most critical measure of a vessel's ability to resist capsizing, and the number resolved on the screen: positive 0.48 meters. A positive metacentric height means the vessel self-rights after being displaced by wave action. It means the hull is inherently stable. The software did not know it was analyzing a vessel described in a Bronze Age religious text. It knew dimensions, estimated timber density, and waterline position. By those inputs alone, the hull was stable in wave conditions up to sea state 6, significant wave height 4 to 6 meters, the upper boundary of what the World Meteorological Organization classifies as a very rough sea. A modern cargo vessel of equivalent displacement, approximately 43,000 tons, typically achieves a metacentric height between 0.3 and 1.5 meters depending on hull geometry and loading condition. The Genesis specification produced a value squarely within that operational range. That is not a theological finding. It is a calculation. And it is one of 4 engineering findings in the peer-reviewed naval architecture literature that are considerably more interesting than either the devotional or the skeptical position on this vessel has previously acknowledged. Because the engineering analysis of the Ark's specifications does not produce the result that either side expects. It does not produce a vessel that is miraculous, defying physical law through intervention. And it does not produce a vessel that is impossible, a fantasy whose dimensions betray pre-scientific imagination. It produces a vessel whose specified proportions solve the primary structural engineering problem of large wooden hulls with a precision that requires explanation regardless of one's position on their origin. And it produces a vessel whose construction at the stated scale raises engineering questions that the specifications themselves do not answer. The faithful position is more complicated than it appears. The skeptical position is more complicated than it appears. The engineering record is what it is, and it begins with a drawing. The drawing exists in several versions now, produced independently by naval architects in South Korea, Australia, and the United States, each working from the same 6 verses, each applying the same conversion factor, each arriving at the same hull form. A scaled cross-section of the Ark's hull at midship, showing outer planking, 3 internal decks, structural framing geometry implied by the timber specifications, and the waterline at the estimated displacement. The hull form is that of a displacement barge, flat-bottomed, or very nearly so, with a high length-to-beam ratio producing a vessel optimized not for speed or maneuverability, but for stability under passive drift conditions. The 3 internal decks divide the hull volume into 4 horizontal zones. The waterline sits approximately 9 to 10 meters below the deck line, producing a freeboard of 3 to 4 meters, sufficient to prevent wave overtopping and conditions up to sea state 6 at the hull's calculated natural roll period. And the hull's proportions are not arbitrary. The length-to-beam ratio is 6 to 1, 300 cubits divided by 50 cubits. In 1993, a research team at the Korean Institute of Ship and Ocean Engineering, known by its acronym CRISO, published a study titled Safety Investigation of Noah's Ark in a Seaway. The study applied modern naval architecture stability methodology to the Genesis dimensions. Among its findings was a systematic comparison of hull stability across a range of ratios from 3 to 1 through 15 to 1 at the Ark's specified depth and displacement. The finding was unambiguous. The 6 to 1 ratio produced the optimal combination of stability, structural strength, and seakeeping performance across the full range of tested sea states. Not adequate performance, optimal performance. The ratio that minimizes longitudinal bending stress while maximizing transverse stability in a displacement hull of this depth and tonnage. It is the ratio that a modern naval architect would independently specify for a minimally crewed livestock carrier designed to survive extreme sea conditions under passive drift without propulsion or active stabilization. That ratio appears in a text composed, by the most conservative scholarly dating, no later than the 6th century before the Common Era. It appears without any stated engineering rationale. It appears as a simple dimensional specification, and it is correct to the optimization peak identified by computer-aided analysis conducted 3,000 years after the specification was written. Genesis chapter 6 contains 6 distinct engineering inputs. They are worth enumerating precisely because the precision of the specification is itself a data point. The first input is the material, gopher wood pitched inside and out. The Hebrew term gopher appears only once in the entire Hebrew Bible. Scholarly proposals include cypress, with documented use in ancient Near Eastern shipbuilding and excellent rot resistance, cedar of Lebanon prized for large-scale construction, and various resinous softwoods whose natural resin content provides inherent water resistance. These candidates bracket timber densities from approximately 400 to 550 kilograms per cubic meter, bending strengths from 40 to 90 megapascals, and compression strengths adequate for calculated loads. The waterproofing agent, universally identified as natural bitumen, has archaeological attestation in maritime applications dating to the 4th millennium before the Common Era, well within the period framework of the Genesis account. The second input is the overall dimensions, producing at the conservative cubit a hull of approximately 40,000 cubic meters internal volume. The third input is 3 decks dividing the interior into 4 usable levels. The fourth is the internal compartmentalization, the ken rooms. That word is significant. Its primary meaning throughout the Hebrew Bible is nest, specifically a bird's nest. A bird's nest is not a box. It is a woven, interlocking, distributed load structure deriving strength from the interlocking of its constituent fibers rather than from the rigidity of any single member. If the term was chosen to describe an internal framing methodology, and the Hebrew Bible is a text in which word choice is, by scholarly consensus, extraordinarily precise, then it implies a construction technique based on interlocking distributed load framing rather than simple compartmental subdivision. The fifth input is 1 door in the side, a stress concentration point requiring reinforcement. The sixth is the tsohar, an opening at the top measuring 1 cubit. These 6 inputs raise the first engineering question, and it is not whether the vessel could float. The stability analysis answers that definitively. The question is whether it could hold together, because at 133.5 meters, this would be the largest wooden vessel in human history, and the engineering record of every large wooden vessel actually constructed tells a consistent and sobering story. The largest wooden sailing vessel ever built was the 6-masted schooner Wyoming, launched in 1909 at 100 meters. She was constructed with the finest available materials by experienced shipwrights using techniques refined over centuries. The Wyoming leaked. She leaked continuously from the day she was launched until the day she sank in a storm off Massachusetts in 1924. Her hull could not prevent seam separation caused by longitudinal flexing under wave loading. A steam-powered bilge pump ran 24 hours a day. The crew of the Wyoming described the sound of the working hull under wave loading as a continuous, deep groan audible throughout the vessel, the sound of oak frames shifting against oak planking, seams opening and closing with each passing wave. Water finding its way through gaps that were never designed to exist, but that the physics of a 100-meter wooden hull inevitably create. The failure mode was hogging, the tendency of a long hull to flex upward at bow and stern relative to midship under wave influence, causing planking seams along the upper hull to open progressively. The Pretoria, at 97 meters, showed the same failure. So did virtually every large wooden vessel that approached 90 meters. The Chinese treasure ships of Zheng-He, estimated by some historians at 120 to 140 meters, required extensive internal bulkheads if they achieved those disputed dimensions. The Ark's specified length exceeds the demonstrated failure threshold by 33%. The specifications create the problem. The question is whether they also contain its solution. The answer, according to the engineering analysis, is that they contain the critical elements of it. The 6-to-1 ratio is the first and most significant. In a displacement hull, the longitudinal bending moment causing hogging is a function of the length-to-beam ratio, depth, and wave conditions. A wider hull distributes bending load across a greater cross-section, reducing peak stress. 6-to-1 minimizes longitudinal bending for a hull of this depth and displacement while maintaining transverse stability for extreme conditions. A ratio of 10-to-1 would reduce bending further but compromise stability. 3-to-1 would maximize stability but increase beam C exposure. 6-to-1 is the optimization point. The second element is the 3-deck layout. 3 horizontal decks spanning the full length and beam function as longitudinal stiffeners, structural members resisting bending deflection. Each deck acts as a diaphragm, distributing wave loads across the full cross-section, rather than concentrating them in the outer planking. A single-deck hull at this length would experience hogging deflection orders of magnitude greater. The specification is not merely space planning, it is structural engineering. The third element is the Ken compartmentalization. If constructed as interlocking timber framing, each compartment functions as an independent structural cell, distributing loads locally rather than transmitting them through the hull. This is the principle behind modern composite construction, distributing stress across many small structural elements. The egg crate structure of a modern warship's double bottom operates on the same principle, designed to absorb and distribute impact loads. The nest analogy is structurally precise. Collective strength through interlocking members whose combined resistance exceeds any individual component. At the arc scale, this approach would create a whole whose hogging resistance derives not from the rigidity of its outer shell, but from the distributed load bearing of its internal structure. None of these solutions are spelled out as engineering rationale. They are present as dimensional specifications and construction terminology. Whether they were understood as engineering solutions or simply transmitted as instructions is beyond what the analysis can determine. What the analysis confirms is that the solutions are present and correct. The third engineering problem is waterproofing. The instruction in Genesis 6:14 is explicit. Cover it inside and out with pitch. Natural bitumen is a viscoelastic hydrocarbon occurring in seeps and deposits throughout the ancient Near East, particularly along the Tigris and Euphrates, exploited for construction waterproofing since at least the 4th millennium before the Common Era. The archaeological record is extensive. Bitumen-coated reed boats, sealed brick foundations, waterproofed storage vessels. The material's critical property for this application is flexibility. It retains dimensional compliance across temperatures from -10 to 60 degrees Celsius, accommodating the movement that occurs in timber under varying moisture and loading without cracking. A rigid waterproofing membrane applied to a working hull cracks at seams as the hull flexes, creating water pathways at points of maximum stress. Bitumen deforms with the timber, maintaining its seal across the full range of structural movement a wooden hull experiences. The black, viscous material, applied hot, penetrates the wood grain at the surface and forms a membrane that moves with the wood rather than against it, carrying the faint petrochemical smell of crude asphalt, a smell that would permeate the hull's interior spaces and mix with the smells of timber, livestock, and bilge water for the duration of the voyage. Interior application? Waterproofs deck surfaces against animal waste, critical for a livestock carrier. Exterior application provides hull waterproofing. Dual application encapsulates the planking, reducing moisture absorption, and the dimensional changes causing seam movement. Total planked surface area including decks exceeds 12,000 square meters. Coating at working thickness of 10 to 15 millimeters requires approximately 150 to 200 cubic meters of raw bitumen, well within documented Near Eastern deposit capacity. The specification is adequate and specific to the vessel's dual requirements. The fourth problem is ventilation, and it produces the most technically surprising result. The tsohar at the hull's apex measures 1 cubit, 44.5 centimeters. Its engineering function is determined by physics, regardless of its linguistic translation. An opening at the top of a sealed 13.35 meter structure containing thousands of metabolically active animals. This configuration produces stack effect ventilation. When interior air is warmer than exterior, as it would be with 14,000 animals generating metabolic heat, warm air rises and exits through the top opening, drawing cooler air in below. The driving variables are the height differential of 13.35 meters, the temperature differential of 10 to 15 degrees Celsius above exterior, and the opening area. The calculation produces an air exchange rate of approximately 0.1 to 0.3 changes per hour. Modern livestock vessel standards specify a minimum of 0.1. The tsohar system produces rates at the lower boundary, adequate for maintaining breathable air quality and preventing toxic ammonia and methane accumulation, not for optimal comfort. On the lowest deck of the hull in sea state 6 conditions, the experience would be the 12 to 15 second roll period, the sound of water against the hull at the waterline, the smell of bilge and animal and bitumen in a sealed space, and the specific quality of air that has passed through thousands of animals before reaching the ventilation outlet. The ventilation is consistent with a finite emergency voyage, not permanent habitation. The dimensions and position of the tsohar produce this result. They are not arbitrary. The physics generate operational ventilation from a specification written millennia before the underlying thermodynamics were formally described. The hull works. The structure addresses its primary failure mode through dimensional optimization and internal framing. The waterproofing is documented adequate technology. The ventilation meets minimum standards. The engineering analysis has reached the boundary between naval architecture and logistics. The questions that remain are not about the hull, They are about everything inside it. For the complete technical record, every stability calculation, structural reference, and comparative data point, the pinned comment contains the full documented breakdown of all 4 engineering problems and the logistics analysis that follows. The logistics analysis begins with a taxonomic question. The modern inventory catalogs approximately 8.7 million eukaryotic species. The suggestion that the Ark carried representatives of every modern species appears nowhere in the primary text. The Hebrew word for the categories brought aboard is min, translated kind, corresponding roughly to the taxonomic family level. Baraminological research estimates approximately 1,000 to 2,000 terrestrial animal and bird kinds encompassing current diversity. At 2,000 kinds with the clean and unclean ratios of Genesis 7, the estimated population is 7,000 to 16,000 individuals. The analysis uses 16,000 as the upper bound. A juvenile selection strategy, implied by practical requirements, reduces average body mass to 10 to 20 kilograms. Juveniles consume less food, produce less waste, require less space, tolerate confinement better, and carry longer reproductive lifespans. At this size, 16,000 animals total approximately 320,000 kilograms of mass. The Ark's internal volume of 40,000 cubic meters is 87% of the Titanic's gross volume. 16,000 juveniles at 1.5 cubic meters per animal, consistent with modern transport standards for this size class, require 24,000 cubic meters, 60% of total volume. The remaining 16,000 cubic meters must cover food, water, crew habitation, walkways, equipment, and waste management. This is a tight logistics profile comparable to modern livestock vessel ratios on extended voyages. The food requirement is the critical constraint. At minimum metabolic maintenance rations, 16,000 animals averaging 15 kilograms need approximately 80,000 kilograms of dry feed daily. Over 371 days, that totals 29.7 million kilograms. At stored densities of 400 to 600 kilograms per cubic meter for compressed hay and dried grain, this requires 50 to 75,000 cubic meters. That exceeds total volume. At the upper population estimate with standard rations, the food does not fit. This is the first point where the logistics analysis identifies a constraint the specifications do not resolve. But the variables move the boundary substantially. At 7,000 animals, food storage drops to 22 to 33,000 cubic meters, which fits with room remaining. Grain-heavy diets reduce volume per calorie by a factor of 2 to 3. Natural metabolic reduction in confined low-stimulation environments, documented across multiple species, cuts caloric requirements by 20 to 40%. These adjustments produce a range from operationally feasible at the lower population estimate to severely constrained at the upper. Food storage is the most sensitive parameter in the entire model. Water: 16,000 animals require approximately 48,000 liters daily, 17.8 million liters for the full voyage, needing 17,800 cubic meters of storage. Rainwater collection across 3,000 square meters of deck at even modest precipitation rates provides meaningful supplementation. In the storm conditions described in the narrative, rainfall rates would be substantially higher. Water is a significant but less constraining variable than food. Waste: approximately 12,000 kilograms solid and 16,000 liters liquid daily. The 3-deck layout provides gravity-based drainage through sloped surfaces to scuppers at the waterline, the standard method in livestock vessels from antiquity through the 20th century. Interior bitumen coating prevents timber degradation from continuous waste exposure. The system requires regular manual cleaning but no mechanical processing. Waste management is operationally adequate for the mission. The crew specification is the most significant unresolved logistics problem. Genesis specifies 8 people. Modern livestock operations require 1 handler per 500 to 1,000 animals, meaning 16 to 32 crew minimum at this population, plus vessel operations personnel. 8 is 25 to 50% of the minimum modern requirement. The analysis does not declare this impossible. Modern standards are calibrated for commercial operations with regulatory oversight, not for survival conditions. Minimum viable care, feeding, watering, and gross waste removal without individual animal monitoring could theoretically be managed by 8 experienced handlers working sustained shifts with a physical plant optimized to minimize labor. The Ken compartments, configured with integrated feeding troughs and gravity waste channels, would reduce per animal labor to the necessary minimum. This is the absolute lower boundary of feasibility, requiring optimistic assumptions about design efficiency and crew endurance for a year-long voyage. The engineering record of the Ark, treated as testable specifications rather than as theological proposition, contains findings that complicate both positions with precision. The hull dimensions produce a stable, seaworthy vessel confirmed by peer-reviewed analysis from institutions on 2 continents. The 6-to-1 ratio minimizes the primary structural failure mode and maximizes passive stability. appearing without stated rationale and validated by computational methods developed millennia later. The bitumen waterproofing is documented adequate technology from the geographic region of the account. The ventilation produces minimum viable air exchange through passive physics dependent on the specific dimensions described. These findings are confirmed. The hull works, the proportions are correct, the waterproofing is adequate, the ventilation is feasible. The logistics analysis produces a range depending on the biological assumptions. At the lower population estimates, the profile is feasible. At the upper estimates, food storage and crew capacity are the constraining variables. What the record cannot confirm is equally specific. Construction methodology for a 133.5 meter wooden hull with ancient tools is undocumented. No comparable project exists in the archaeological record. Gopher wood remains unidentified. The 8-person crew is the parameter with the least margin, the specification requiring the most optimistic assumptions to bring within feasibility. The cross-section drawing sits on the table where it was produced. A hull form derived from 6 verses of ancient text, analyzed by software that computes stability without knowing origin, confirmed by calculations that apply equally to a modern barge and to the most discussed vessel in human literature. The hull is stable, the proportions are optimal, the waterproofing is sound, the ventilation meets minimum standards, the carrying capacity is constrained but defensible at the lower biological range. Construction methodology and crew logistics are the open questions, the points where analysis reaches its limit and the specifications fall silent. The drawing does not resolve the argument about the ark. It refines it. It replaces opinion with calculation. And the calculations produce a vessel more competently specified than any position in the cultural argument, in either direction, has previously had reason to acknowledge. The numbers are in the record. What they mean beyond what they calculate is a question the drawing was never designed to answer.